Okay, so here's what we were talking about last time. We were talking about directional derivatives. A quick reminder, so the stuff we're doing today is not fair game for tomorrow or for Wednesday's midterm exam. But it is fair game for the second midterm exam. And so we have to cover it eventually, and today is that day. So anyway, it's a little weird. Anyway, this is what we were talking about last time, directional derivatives. It's a variation on just how you can use the chain rule to interpret the chain rule as a relationship between input velocities and output velocities. Right? This is a nice interpretation, or input changes and output changes in whatever form. So the variation is that if we consider only real valued functions, then this is a single row. The matrix is a single row, and so you can interpret it then as a matrix, as a vector dot product, and this gives you this formula. So, if you're only dealing with one, with a real valued function, this is a handy formula to remember. Okay, now this is, again, still kind of the chain rule, right? So the term directional derivative is a further special case of this. Directional derivative says, what if the vector representing our input change, or input velocity, I like to think of them as velocities, is a unit vector. Right. Now I spent a bunch of time last time talking about how that is one interpretation of the term directional derivative, and I don't want to go off into the cultural consequences, etc. But that is the interpretation that we're taking in this Math 212 course. I will just very quickly remind you that heads up, not everyone interprets this term the same way. But anyway, in Math 212, the input velocity has to be a unit vector. Okay, and again, the idea there is look at the word direction. It's sitting right inside of the term directional. And how do we represent directions? Well, we represent directions with unit vectors. So it's reasonable. Okay. All right. So we've talked about this. It's a special case of the chain rule, right? Now here's a different point of view on it. It's a generalization of the idea of a partial derivative. You look at it just the right way. Let's consider what happens if you take a directional derivative where your unit vector representing your input velocity is a standard basis vector. What happens? Okay, well, standard basis vectors are really easy to represent numerically. It's a bunch of zeros with a 1 in a single position representing which direction, along which axis are we looking? And that dot product is easy to compute, right? A dot product with a bunch of zeros, pretty much all the entries in the gradient get multiplied by 0, except for this one. Whatever entry in the gradient matches up with that 1. So what you get is literally a partial derivative. So when you are looking at this special case of a directional derivative, namely that your unit vector is a standard basis vector, you literally get a partial derivative. Saying that backwards, a special case of a directional derivative is a partial derivative. Saying that backwards, a generalization of the idea of a partial derivative is the idea of a directional derivative. So, partial derivatives say, look, at unit speed in the direction of any axis, and look at what is the corresponding output velocity. One interpretation of a partial derivative. Directional derivative says, okay, well, same idea, but let's just not confine ourselves to looking along an axis. Let's look in unit vector, of course, but look in any direction. What do you get? Okay, so now here's a very valuable interpretation. And by the way, this is only if you're looking at a unit vector. So this is a nice justification for this point of view that the book is taking, that the term directional derivative should be reserved, just unit vectors. Here's a nice justification. So don't forget, you can interpret velocity as a unit vector times a speed. Now, in fact, any vector can be viewed as a unit vector times a magnitude. Right? Velocity, the magnitude is speed. Okay, so let's take that formula, right? And let's just apply this idea of a directional derivative. Remember, so dot product With a vector, chain rule gives you a rate of change. So this is one of the first formulas we wrote down today. Dot product with the gradient gives you the rate of change. df dt. If v is representing your change of position with respect to time, right? Then this dot product gives you rate of change of the function with respect to time. Okay. Don't forget also this scalar factors out of the dot product. Furthermore, that scalar, the magnitude of the velocity vector, speed, is ds dt. It's distance per unit time. Right? So now let's look at what we've got. This is equal to whatever that is times that. Well, it's easy to figure out what that thing is, right? I mean, just by the single variable chain rule, this has got to be df ds. And this, of course, we recognize as the directional derivative. So, nice punchline then. Directional derivatives can be thought of as rate of change of the function with respect to distance. Right? It's nice. This is a different idea. This formula allows us to interpret rate of change of the function with respect to time. If you want to compute rate of change of the function with respect to time, there you go. Right? Dot product, the gradient with your velocity vector. Maybe you're driving along the road, right? And you want to know, okay, as I'm driving along the road, how fast is my altitude changing? How many feet of altitude am I gaining per unit time? Reasonable question, right? Your own personal experience. What we're talking about here, df ds, this says, forget about your personal experience. This isn't, give me 2 seconds. This isn't about your personal experience. I want to talk about the road itself. Whether you're driving fast, whether you're driving slow, that's your thing, right? But I want to know the road itself. Per distance that you travel along the road, how much does altitude change? Right? That's telling you something intrinsic to the road. Again, another road versus road trip kind of situation, right? Something intrinsic to the road is how steep is the road. And that's independent of how you drive on it. Right? So this is a very natural thing to want to talk about. What is I can't get the little thing. What is df ds, and the directional derivative totally computes it. Yeah, you had a question. I'm sorry.
So what does f represent?
Whatever function we're interested in for whatever reason. So in my little metaphor, as we drive and we're trying to keep track of how altitude changes, f is altitude. But it could be anything. And so given a domain through which you might be moving, right? Maybe I'm here, maybe I'm moving with, along some path like that with some velocity. Who knows what that function is? Lots of different things.
Yeah. So f is a function of s, and s is a function of t?
Well, f is a function of position. Right? Now, when we write down something like df dt, this is sort of implicitly saying f is a function of position and position is a function of time, right? When I write down something like df ds, that's saying as I move along some path in the domain, my position is a function of my total distance traveled, and that's what you sort of compose with, right? Okay, so this is an interesting object. It's the road versus the road trip, right? And it's computed with directional derivative. Yeah.
The page before this, you said you could interpret the directional derivative as df dt. So why is it df ds down there?
Yeah, well, so that's right. So this is df dt if, with the understanding that your velocity is a unit vector. And if you think about it, if your velocity is a unit vector, that means the magnitude of your velocity is 1. That means that your speed is 1. That means that ds dt is 1. And that means that df dt and df ds are the same. Yeah, no, it's a great question. Yeah, right, absolutely. Did everybody follow the question?
Yeah, I don't like where the S came from.
Yeah, it's just a notational choice. I am talking about, as you move along some curve, right? So, and let's say this is our starting point. Then S represents the total distance that I've traveled along that curve from the starting point. Does that make sense? So it just represents, it's the odometer on my car. Total distance traveled. That's all. Yeah. It's the same S that we've talked about when we were talking about parametric curves and curvature and all that kind of stuff. Same S. Yeah. Everybody good? Okay, related to that, we've already kind of talked about this. My metaphor up here was thinking about a road and, how fast is my altitude changing? And let's talk about, something intrinsic to the road, how much altitude the road gains per unit distance, not surprisingly, would be the slope of the road, right? How steep is the road? Well, this is just an observation that's one takeaway from the above. So if you are moving around down here in the domain, and you look at your corresponding path up there on the graph, right? Then per unit distance traveled, let's see, as you're moving with, that velocity, you're moving in that direction. That's the distance that you travel along the road. That's ds. That's the height that you gain. Well, that's df. And you can see that this directional derivative then, right, that df ds that we just showed the directional derivative is equal to, is the slope of that particular cross-section of the graph. So, another nice fact, another connection to partial derivatives, that directional derivatives, just like partial derivatives, are slope of a graph. It's just slope of a graph in whatever direction you're going, not necessarily in an axis direction. Okay. All right, so let's see an example. Suppose I have, temperature is given as a function of position. This isn't implausible, right? Maybe I know in this room, for example, I know what the temperature, it's a little colder over there, maybe by where the air conditioning comes out, maybe a little warmer by the window, something like that, right? So there's a variation of temperature in this room. And suppose I've got a little gnat, and he's right here, right? And he wants to know, from this location, what is the rate of change of temperature with respect to distance traveled? Now, he's moving along a particular path. So he's at this point, and he's moving, along some sort of a curve. So he's at this point moving with some given velocity. With that velocity, he could just dot product with the gradient to find what the rate of change of temperature with respect to time is. Dot product with the gradient, sure, right? But he wants to know what's the rate of change of temperature with respect to distance, right? So he's like, look, I'm doing a lot of flying here. How much, as I fly, per unit distance that I fly, leave it to me to decide how fast I want to fly, right? But per unit distance that I fly, how much increase in temperature am I going to experience? Right? Very reasonable question. And Nat's asked this question all the time, so I understand. Kidding. Here we go. This thing that we want to compute is the directional derivative. Right? So dot product with the gradient vector, unit vector representing the direction you're going, easy to compute, velocity divided by its own magnitude. Right? And there you go. Now, what would have been the alternative? One way you could have approached this, sort of a chapter 12 approach to this problem might have been, look, if I take temperature as a function of position, and if position is a function of time, I could compose those, but that's going to allow me to compute, when I differentiate, that's going to allow me to compute derivative of temperature with respect to time. And I don't want temperature with respect to time. I want the derivative of temperature with respect to distance. So do I need to reparameterize and come up with, position as a function of s, and then play this game, and then say, okay, well, then I'm looking for, temperature is a function of position, and position is now a function of s, and then I could use, I could take a derivative and get dTds. Right, so this would be kind of a brute force way to answer the question. You would have to reparameterize the curve. That's annoying. Right? It's work. It's effort. I'd have to compute arc length. That's an integral. Right? So this is much more work than necessary. This is a much nicer alternative. Get this thing. Okay. All right. Now here's a different situation where it might be convenient to use this concept. So suppose we're moving with a certain velocity. Note that's not a unit vector, and so your first instinct might be to think, okay, well this has got nothing to do with directional derivatives. We're not moving with a unit vector velocity, right? The question: compute the rate of change of temperature with respect to time. Again, not obviously in any way connected to directional derivatives. And it would seem like I could, maybe just use the old formula, the chain rule, right? Well, quick observation. Now, it's not like this is going to save you loads and loads of effort, but this is still a nice streamlining of the process. Note that this thing that you want can be written as this product. Note that dTds is a directional derivative. Note further that I'm in the direction, not just a unit vector, but in the direction of a standard basis vector. And because this is a standard basis vector, that directional derivative is a partial derivative. World's easiest derivative to calculate. Right? So this is a nice observation. Anyway, not a big deal. I mean, the gradient wouldn't be that bad to write down, but a gradient's made up of a bunch of partial derivatives. Now we've got it down to one partial derivative. Anyway, whatever that's worth. Okay. All right. Now, next observation I want to make is just a kind of a psychological phenomenon, but there's a tendency for students to look at material that comes in the course and assume that later material is more powerful and therefore superior to earlier material. And here we are learning about the directional derivative after we learned about the chain rule. And so some students, this happens, think, okay, well, this must be the new and improved replacement, for the chain rule that we will never have to use again because, well, of course, this is the new one. We're presenting it later. Why would I present something inferior, right, after something that's better? That wouldn't make any sense. So students sometimes think it's got to be better, therefore I should always use this. And I just want to address that point and point out that it is absolutely false. You don't have to use it. It is not better. It's different, right? It's just a different, it's just an observation. It's a tool for your toolbox, as I like to say sometimes. So sometimes it is convenient to use a directional derivative. Sometimes the question you have been asked, how steep is this road? What's the rate of change with respect to distance? Whatever. What's the slope of the graph of the function? Sometimes the question you have been asked is about the directional derivative. But sometimes it's not. And sometimes it's not particularly convenient to use. Don't just reflexively use it because, you feel like maybe you're somehow supposed to or something like that. So here's my example. So suppose some velocity is given, some, whatever, random vector. And you want to compute the rate of change of some function capital T with respect to time. Here's how you would do that with directional derivatives. Derivative with respect to time, right? dTds, ds, dt. dTds is the directional derivative, as we've just discussed. ds dt is speed, magnitude velocity vector. Fine. What is this unit vector? The unit vector in the direction of your velocity. Well, look at that. It's the velocity divided by its magnitude. And so look at how ridiculous this calculation is. Right? We're taking our velocity vector. We're computing its magnitude. We're dividing by that magnitude. We are then subsequently multiplying by that magnitude to absolutely no effect. What's the point? Right? The alternative is to use the chain rule. Here's how the chain rule would break this calculation down. You want to compute dt dt? Cool. Boom. Right? So which resulting formula which is the better formula to use in this case? I claim that this is a double waste of time. You've got to compute a magnitude, which involves a square root, and then you've got to multiply by it, and then you've got to divide by it. It's arguably 3 steps that amount to absolutely nothing. Right? So anyway, think about what you're doing. Think about why you would choose to go one route versus another, and don't make a pointlessly difficult path for yourself. Does that make sense? Okay. All right, so going back to these examples, why did I use directional derivative here in this case? Oh, because something cool happened. That vector being a standard basis vector, making a connection to directional derivative made my life easier. That's why I did that. Right? What about in this example here? Why did I make a connection to directional derivatives? I didn't even really have a choice. Here I was asked for a directional derivative. That's what the question was about. Right? Okay. All right. Okay, moving along. Let's see here. Let's go back to this first page here. Here's our formula for directional derivatives. Right, dot product with the gradient vector. Where does the gradient vector come from? The gradient vector is this vector of partial derivatives. It's the rows, if you will, of the Jacobian matrix. Right? We've written it down for algebraic purposes previously. It's a tool that we use to compute differentials, right? Linear approximations. It's an algebraic thing, right? It's something that up to now in this course we view it as being an algebraic convenience. To write, a vector whose coordinates are the partial derivatives is algebraically, notationally convenient. Very compact. Okay. All right. So what I want to show you now is that, in fact, this gradient vector has a geometric interpretation. And it's unexpected how this comes up, but it is very cool to know. So I'm going to start with a question. Suppose you have a differentiable function. Here we are. There's our differentiable function. We're at some point in the domain. And let's see, what does this function represent? Well, maybe altitude, maybe temperature, right? Lots of different things it could be thought of as representing. And here's a reasonable scenario. Suppose that, being at this point, I would like to know what direction should I start moving if I want to make this function increase as fast as possible. So maybe my location represents position on a map. I'm mountain climbing, and I want to get to the top of the mountain. I want to go uphill, right? That's how you climb mountains. Don't walk down. Right? Right. So what direction is uphill? I mean, a rough approximation. That's how you'd climb the mountain. Another scenario. Maybe I'm cold, right? And this function f represents a temperature, and I want to know which direction should I be moving to increase temperature as fast as possible. And now, I want to restrict my question to unit vectors, u, because I already know the second half of my answer. If I want to warm up as soon as possible, I know how fast I should run. I should run as fast as I possibly can, right? Make sure you're running in a direction in which temperature is increasing, and then faster is always better than slower. Of course, right? So that's trivial. But which direction is a non-trivial question, right? Okay, so to maximize this directional derivative, very relevant question. Okay. So how do we do that? Well, let's look at this directional derivative. We have a formula for how to compute the directional derivative. Here it is. It's a dot product. By the way, here's how you compute dot products. Right, so this thing that I want to maximize the directional derivative. Well, okay, that means I want to maximize this expression here. I want to maximize that. And keep in mind, I want to maximize that expression over all possible unit vectors u, all of which have magnitude equal to 1. Okay, so really I want to maximize this expression. I mean, it's got nothing to do with the fact that an extra factor of 1 doesn't do anything. Okay. So I want to maximize this expression. What about the gradient of f? How does this play into the question here? Well, I want to maximize that expression over all unit vectors. Notice that the gradient of f doesn't have anything to do with what direction am I pointed, right? The gradient of f is just some vector. And whether you're choosing to go that way or choosing to go that way or choosing to go that way, the gradient of f only depends on f. It doesn't depend on which direction you are facing. Right? Does that make sense to everybody? So this is a constant. So what I really want to maximize then is this. I want to maximize cosine theta. I want to maximize this angle right there. Right, over all possible unit vectors, what's going to make cosine theta as big as possible? And I remind you of trig. Biggest value that cosine theta can take is 1. It takes that value when theta is 0. This is what it looks like when theta is equal to 0. Right? And specifically then, U points in the same direction as gradient f. Yeah? Does that make sense to everybody? Neat little calculation. Okay. All right. So there you go. There's your function. Your vector representing what direction the function increases the fastest. Okay. All right. So by the way, this is a geometric fact, right? This is a geometric characterization, you might say, about the gradient vector. Previously, the gradient vector was just kind of an algebraic convenience, a notational shorthand to represent, algebraically that you're going to take a bunch of partial derivatives and assemble them a certain way. Here we see the gradient, the direction, that intrinsically geometric feature, right? The direction of the gradient is something natural. It points in the direction in which the function's increasing the fastest. That's geometric knowledge. Cool. Okay. All right. Here's a natural next question. Okay, so we've agreed which direction I'm going to run. All right. I'm going to move that way. Right. I'm going to move in the direction in which the function's increasing the fastest. Okay. To what benefit? Right. How fast am I going to be getting warmer? How fast am I going to be climbing the hill? How fast is the function changing as I move in that direction? What is the rate of change per unit distance traveled? Okay. Well. So again, this is how you compute that directional derivative. That is magnitude squared. So this boils down to magnitude squared divided by magnitude, which of course is magnitude. So another easy calculation and another geometric interpretation of the gradient vector, if you think about it. So again, what is this gradient vector? You assemble it a certain way, partial derivatives, notational convenience. But the direction it points, geometric feature, means something. And now we see that the magnitude of it, another geometric feature, means something. It says the magnitude of the gradient tells you how fast is the function increasing in the optimal direction. So this is a neat little collection of observations, so that's what I have here. So this is what I call a completely geometric characterization of the gradient. Previously described as an algebraic construction, the gradient has direction and magnitude that means something. The direction is the direction of fastest increase. The magnitude is the rate of change in that direction with respect to distance traveled. Geometrically natural. We're not characterizing the gradient by what its coordinates are. We're characterizing the gradient by what direction does it point and how long is it in that direction. So anyway, geometric. Okay. All right, here's another neat fact. Very surprising fact. I claim that gradients are always perpendicular to level sets of that function. Very surprising. Hard to see this coming. Here's the justification for why. Suppose you're here. That point. That point the function's got some value. Let's say that value is c. Let's then consider the level set that point is on. Every point in the domain is on some level set, in other words. So let's look at that level set. Okay. Now, let's think about the tangent plane to that level set. All right, so by the way, level set, purple. So let's think about this tangent plane, and let's think about vectors in the direction of that tangent plane. Vectors parallel to that tangent plane. And I ask, how does the function change as you move in the direction of those vectors? Right? Suppose from the point I'm at, I take off and start moving, parallel to the level set, by some small amount. What's my linear approximation to how the function's changing? And I claim 0. Because you're moving along a level set. The whole point to the level set is the function has a fixed value on the level set. If you're moving along a set where the function has only a single value, then you're moving along the set where the function is not changing. So our linear approximation of how the function is changing is that it's not changing. All right, is everybody happy with that? Pretty plausible? Now, don't forget how differentials are computed. Differentials are dot products. Gradient dot dx. All right, so now let's clean up this picture a little bit. For all of these differentials of position, we agree that df is equal to 0 for all of those dx vectors. That means that my gradient has got to be perpendicular to all of those dx vectors. What direction could this gradient possibly point if it's perpendicular to all those dx vectors? Well, it's got to be perpendicular to the surface. Plausible? Everybody happy with that? Okay. So, neat fact. Yeah, here we go. So it's perpendicular to the level set. Okay. Now, one thing to be very careful about, a lot of students will streamline this statement a little too much and say, oh yeah, the gradient's always perpendicular to the surface. Nope. Gradient's perpendicular to level set. Right? It's critical that we're looking at level set here. If you, by streamlining, sloppiness of terminology, try to assert that the gradient is perpendicular to the graph, well, that's terribly, terribly wrong. It doesn't make any sense, in fact. If you think about it, it couldn't make any sense if you have a function from Rn to R1, level sets live inside of Rn. The gradient is a vector in Rn, but the graph is a subset of Rn plus 1. Right? So how could, doesn't make any sense, how could the gradient be perpendicular to a graph? That doesn't make any sense at all. That makes everybody on board? Doesn't make any sense. So don't make that connection. It's level sets that gradients are perpendicular to. Okay, all right. So now, with that said, I would like to address the question of how gradients can help us understand graphs. and this is I'm going to use a trick that I've already made a reference to. So anyway, I'm getting ahead of myself. So here's a function from R2 to R1. That's what the graph looks like. Let me get out of this yellow. Yellow is stressful. There we go. So there's what the graph is. Don't forget, the word graph means equals a new variable, right? That means you're taking the function that you're trying to draw a graph of, you're setting its output value equal to a new variable. It's this very specific construction. Okay. All right, and let's ask the question, how would I find the tangent plane to that graph? Now, we already know the answer. The way we find the tangent plane is argue that, well, look, the tangent plane should just be the graph of the linear approximation. Right? We have f as a nonlinear function. Its linear approximation is that, I think we called it L, right? And you say, look, L and f have to have the same derivatives because, come on, it's an approximation, and so it really should behave just like, and so once you know that it has the same partial derivatives, and you go from there. We wrote a bunch of stuff down. So here's a different approach to how to find the equation of the tangent plane, and it goes like this. This graph is a level set of a different function. Y'all remember this little move? Yeah, it's a little weird, right? Very convenient sometimes. And I made the observation when I presented that you can do this, that a graph of one function is always a level set of a different function constructed in this way. And I said, look, the time is going to come where we understand the calculus of level sets in a really nice way, for which there is no corresponding understanding of the calculus of graphs. And here we are. We understand the calculus of level sets very nicely in this sense, and that is level. What's up here? Level sets are always perpendicular to gradient vectors. All right, so this is, I like to call this a statement about the calculus of level sets, because gradients are calculus. Yeah. Okay, so we find ourselves looking at a graph, and we think, well, that's a graph. As written, it doesn't look like a level set. So I reinterpret it as a level set. Now, even though technically I'm interested in this surface as being the graph of f, I can choose temporarily to view this as, look, it's a level set of that function. I understand calculus of level sets. And so I can make this statement that the gradient of that function will be a normal vector. Right? That's what it said on the previous page. Gradients are perpendicular to level sets. Perpendicular. Everybody on board? All right. Okay, well, gradients are easy to compute. There's how you compute that gradient. Right? Now you take this function here, g, take its partial with respect to x, partial with respect to y, partial with respect to z is a freebie because there's a z right there. Okay. And then everything else kind of falls into place once you know that this normal vector is that, right? This point, let's see here. Let me zoom out a notch. We're looking at a graph. So here's the point that we're interested in. If you're interested in, above the point a comma b, well, z is f of x comma y. So the point we're interested in on the graph is a comma b comma f of a b. That's our x naught. And just multiply it out. Multiply it out. And this equation turns into our familiar equation of the tangent plane. So it's the same answer that we got doing it the different way, different argument. Anyway, this is a nice argument to think about. Shows how to take advantage of this property of the gradient. Forces you to recognize, make sure that you can understand how a graph could be reinterpreted as a level set of a different function, right? To nice effect. So, not a lot of nice things about that calculation. Okay, let's see here. Okay, we're doing pretty good on time. Good for me. Usually I'm going slower than this. So we are going to dip our toes into Chapter 14 now. Just a little bit. And then, of course, test on Wednesday that will have absolutely no Chapter 14 in it. Right? Yeah. I need to think about that. I think so. Yeah. So here's why, right? So this material that we're talking about today, right? I don't expect you all to work on these homework problems today. You've got an exam to study for, right? So sure, right? But all of this stuff that we're doing today that will be, part of the homework assignment that's going to be due Friday, you can certainly start at, you can treat Wednesday's exam period as effectively being when you first see this material, right? And so you'll have the same 48 hours to do those homework questions starting after the exam that you would otherwise if it had been presented on Wednesday. So I think it's reasonable. So so we'll have homework due on Friday in the usual schedule. But again, my advice, maybe don't start today's material until Wednesday. Everybody happy with that? Everybody understand the rationale? Maybe I should say it that way. Yeah. Yeah. Happy was the wrong word. Okay. Okay. So integrals. I want to spend a few minutes talking about single variable integrals, make sure that everybody understands what single variable integrals are. There's a lot of common misunderstandings, a lot of little fibs that get told to students in single variable calculus classes. Sorry? Yeah? Okay, yeah. So the important one here is that integrals are Riemann sums. And this is the big point that I want to make sure we're all good with. And by the way, a bunch of details about Riemann sums. A Riemann sum is this algebraic expression, limit, summation, blah blah. And there's all these little details. Delta x is b minus a over n, and xi, a plus I delta, all that business. So I hope you all have seen all of this. A common misconception is that, and by the way, I thought this too when I was first learning calculus, because the way the material was presented to me was, okay, look, we're interested in this question of what's the area under some curve. It was proposed to me that this is the question. And to that question, the first thing they did is they wrote down a Riemann sum, and I thought, wow, that's inconvenient, right? And then after that, they said, hey, by the way, here's a different way you can do it. Let's make a clever argument about derivatives and note that in this case, blah, blah, antiderivatives and therefore fundamental theorem of calculus. Boom. Much more convenient. And I thought, wow, this Riemann guy, he must not have, he wasn't as good as Newton. Newton came by after Riemann and cleaned up the mess that Riemann had made of it. Right? That's I don't know. That's what I thought when I was learning this material for the first time. Well, minor historical note: Riemann didn't come around until the 1800s. Newton did calculus in the 1600s, so that didn't really make sense, right? So I was chronologically way off there. Okay, all right. So. Why didn't Newton write this down? Why did Riemann have to do it? Given that Newton had already done a bunch of stuff, why did Riemann write this? It was a long conversation of stuff that we can't really go into. But I do want to point out that, why it is that this offers a lot of value outside of the idea of, we're going to compute area under a curve. So first observation I want to make is that area is one of a very large number of applications that can be dealt with integrals. In fact, it's not even a very important one. It just doesn't come up that much. How often is it? I mean, think about engineering problems that you might be, a lot of y'all are engineers, right? Engineering problems that you might face. How often do you really think it's going to be that you really need to know I need to compute the area of that thing there? Hardly ever. Right? It hardly ever comes up, other than trivially, like areas of rectangles, circles, etc. Right? But weird shapes. How often do you really need to compute the area? Hardly ever. So what you need to compute is other stuff like the amount of work that it takes to perform a certain task, or lots of other applications. So I'm just going to talk about work. Okay, this is something that you need to deal with a lot. Right? How much work does it take to blah, 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 blah? Well, now we're talking about how to make a car engine more efficient, right? Car engines burn gas. They perform work. This is all physics-y kind of stuff that's really, really important. Okay, so we're clear on why this is important. Not so much with area. Okay, whatever that's worth. Okay, so how are we going to compute the amount of work that it takes to perform a certain task? Well, what was presented to me, at some point, was that, well, look, work is force times distance, and look, let's consider, we've got this big task that we need to accomplish, but let's consider just little small parts of it, and on that little small part of the task, there's a little distance and there's a corresponding force, and work is force times distance. So we're going to have these expressions that are something times something else, and if you view the first something as a height, and then if you choose to view the second something as a width, then it's like you're computing an area. So the case was made to me that we're going to compute work by way of area. And at this point, let me make the observation of what I think that explanation really was. That explanation was effectively this. This whole business about, well, we want to multiply something times, something that could be interpreted in different ways times something else that could be interpreted as a width. That's kind of putting together a Riemann sum. There it is. There's something times delta x. Right? So if, in effect, we're making a connection to Riemann sums anyway. Yeah? Everybody on board? Okay. So what's the point then? Again, just for, don't copy this down because this is really wrong. I'm going to scratch that out, and I'm going to label area as being the definition of an integral. Why would I do this? Right? What's the point of that? What's the point of making this unnecessary connection to area with nebulous arguments just so I can not have to write down Riemann sums? It doesn't accomplish anything. Right? Area performs no actual role in this argument that I've got this with the blue path. If I'm interested in computing a certain amount of work, I do not need to connect that to area. Right? All I really need... Oh, I didn't want to... okay, here we go. All I really need is to connect work to Riemann sums. Right? And this little additional sort of like a jaunt... oh, and by the way, don't forget, it's area. Completely pointless. Yeah? Everybody on board? Pointless and suspicious. Right? It doesn't really, another related point then. What's the physically natural connection between work and area? It's not. There's no such thing. Right? Work is measured in energy. Area is measured in square inches. There's no connection between those at all. Right? So anyway, there's a common misconception that integrals are about area. It's not. The area application is, kind of cute. It has its, every so often. It's geometrically convenient. It makes for a nice way to visualize. If you need some personal satisfaction in how to think about integrals, okay, sure. I'm not opposed to that, but it's really not a very important part of the process. Riemann sums are what integrals are, because all of these different applications, lots of different kinds of applications, they all directly relate to Riemann sums. No interpretation with area required. We make integrals defined by Riemann sums and then compute Riemann sums with the fundamental theorem of calculus. Okay. All right. Okay, so anyway, so there's that. Now, so this is all single variable calculus. We're in a class called multivariable calculus. Why am I talking about single variable integrals? Well, I want to make sure that we're all kind of on the same page. Sort of a starting point. A lot of what we're going to do in multivariable is going to be a lot of what we're going to do in a multivariable calculus class is generalize. And what it means to generalize something is take a set of ideas and then apply it, in a different, more general setting, right? Or more, a more sophisticated setting. So that's what we're going to do. But before we can apply ideas in this different setting, we need to make sure that we have a clear picture of what is the original concept in the first place, right? So I want to make sure that we're all clear on what single variable integrals are. Single variable integrals are Riemann sums. So we're going to try to generalize the idea of a Riemann sum. I will make occasional, not so important references to area and related geometric ideas. But mostly we're going to be computing Riemann sums. This will be valuable when we're talking about double integrals, but it's going to be indispensable when we're talking about triple integrals. You cannot do triple integrals without fundamentally understanding that integrals are Riemann sums. The area argument will crash and burn. More on that then later. So see y'all later. Have a good Monday. Yeah.